Good. So now I can start.
Yeah.
Recording is on. So
I think so.
yeah, good. So thank you, Jan, for your nice introduction. I'm very pleased to and honored to give a talk on this seminar. It's very bold for me to talk in front of mathematical physicists because I am not a mathematical physicist. I'm a mathematician, and I pretend to do things which are related to physics. And therefore, what I can do is to maybe give a mathematician's point of view on things which are of some interest to also the community or audience of this seminar. So more exactly, my talk is related to the connection of a mathematical theory, which is inverse scattering theory for Schrödinger operators, and Korteweg-de soliton solutions of the Korteweg-de Vries equations. So the talk is here on the slide, and I'd like to mention that this is a result of our joint work with Bogdan Melnik and Jaroslav Mikityuk from Lviv. Okay, so this is a brief outline of today's presentation. So I'll try to recall some interesting history behind the KdV equation and the story of the very famous paper by Gardner, Green, Kruskal, and Mura, which relates these two apparently very distant theories, distant notions. And then I'll briefly discuss one of the possibilities to generalize standard scattering theory to the class of singular potentials. And in the third part, I'll specify some recent progress which we were able to make in this inverse scattering theory and show how it is related to the soliton solutions of the Korteweg-de Vries equation. Okay, so to begin with, most of you probably should probably know the famous story about the Korteweg-de Vries equation, which is not due to Korteweg-de Vries, but as it often happens, the name is not prescribed. The name of the equation or some theory is not given to by the person who was the first to observe this or that phenomenon. In this case, we are talking about the John Scott Russell, which was a Scottish civil engineer, who in August of 1834, so this is a recent occasion when the discovery also has a more or less exact date. So he observed a very unusual phenomenon.
Did you change the slides because the title page is?
Oh,
that's right.
I mean, this sometimes happens.
Okay, but I see already something very different.
Yeah, so I think you should stop sharing and.
Thank you. Good. So I was talking about the observation of John Scott Russell, who observed an unusual solitary wave in the channel of Edinburgh that kept its form and velocity for a very long time. So he then experimentally established some properties of these waves of translations, which are nowadays known as Russell solitary waves, and also reported on them. And this research was then continued or taken up up by Lord Rayleigh in 70s of 19th centuries, which suggested theoretical background for this phenomenon. But in 77 of that century, Bussinesq derived an equation for that solitary wave and more general phenomenon. However, this equation was rediscovered a few years later by Dutch engineers and mathematicians Korteweg and De Vries, and now this equation, famous equation, bears the name of Korteweg-de Vries. This equation is very special in that it is a rare, maybe one of rare situations where a nonlinear partial differential equation admits an explicit exact solution. This is a dispersive PDE, which actually possesses infinitely many first integrals, and therefore this makes it possible to actually derive closed form solutions for its solution. It also possesses many other interesting properties, and in particular, except in addition to the special solitary wave solution, it also has the whole family of so-called n-soliton solutions. And I should now actually change my slide once again, because something is not working. So here is a picture of two solitons interacting in a non-trivial, in very simple way. So as you see, after interaction, the initial higher wave almost resumes its form and velocity is not changed. So this is a very non-trivial interaction of these solitary waves, which is one of the most intriguing properties of this equation. Okay, and now I should swap. Okay, come on. Sorry, once again. So the interest in this KDV was revived after in 1976, Gardner, Green, Kruskal, and Mura found a very interesting relation between of these KDV equation to the spectral theory of Schrödinger equations. Namely, they suggest a very interesting, non-trivial, and very interesting non-linear change of variables, so to say, in these PDE of the following form. So, given the solution phi to KDV, they suggested to consider the family of Schrödinger equations in which this time-dependent solution is potential, and looked at the scattering data of this Schrödinger operator. I'll remind later a few basic things about the scattering theory of these Schrödinger equations, so don't worry now. So it turned out that these time-dependent family of Schrödinger equations, in terms of their scattering data, that is the so-called reflection coefficient, a set of bound states and norming constants, evolves as a first-order linear flow. So it means that we can, given the initial data, we can uniquely solve it for every time. And therefore, we have scattering data at all times, which, applying the inverse scattering theory, allows us to reconstruct reconstruct the potential phi at every time t, and therefore get a solution of this Schrödinger of this KdV equation for every t. So this was this inverse scattering transform technique they suggested back in 1967, and of course this sparked a very big interest in these both the inverse scattering theory for Schrödinger operators and study of KdV. Just in few words, I briefly recall what these scattering data are. So let's take the simplest case of Schrödinger operator, which is minus second derivative plus q of x, which in quantum mechanics describes, it's a typical Hamiltonian for a system which consists of heavy part and a light part. For instance, we can have an atom with a nucleus and electron. Then assuming that potential Q, so that the term Q, which describes the potential energy, is of limited range, in mathematical terms, it means that it is of compact support, then we can consider the corresponding energy equation of this form for energy K square, and find that there are exact solutions outside of the support, and we can single out the so-called Yost solution, which is asymptotic to the pure exponential at large axis. This is a classical notion in this scattering theory. However, this Yost solution gets a physical sense after we divide through both parts by a of k. Then after this division, the solution takes the form of these scaled exponential for large axes, and the combination of two exponentials with plus and minus signs at minus infinity at small axes. And we can interpret actually these as a solution with physical meaning of an incident wave. This is this part e to the power I.A.K.x, which comes from minus infinity. Then it interacts with this potential. And after the interaction part of the wave bounces back to minus infinity, and part transmits to plus infinity. And these coefficients are exactly parts of the waves, and they are called reflection and transmission coefficients respectively. What we discussed were actually left reflection and left transmission coefficients, but we can do the same experiment with the wave incident from plus infinity, and then we'll get two counterparts, R plus and T plus. And then these four objects form the so-called scattering matrix, which has some nice properties. It is unitary for real K. It has some symmetry with respect to the real line. Yeah, so it some coefficient T allows meromorphic continuation in the upper half plane, and so on and so forth. In addition to these scattering matrix, which actually characterizes the continuous spectrum of the Schrödinger operator, there are informations, the data about the discrete spectrum, which is necessarily negative here. So it consists of finitely many negative eigenvalues, bound states. This is certainly minus. And corresponding to them are the so-called norming constants, which characterize, for instance, can be written as the norm of those Yost solutions. At eigenvalues, these Yost solutions are actually asymptotic to decaying exponentials at plus minus infinity and therefore belong to L2. And therefore they give the eigenfunction of that operator. So with that norming, this gives us these norming constants. So what we discussed was about a very special case of interaction potential of bounded range, so of compact spore, but actually in 50s of the last centuries, it was understood that these can be generalized to much wider class of potentials, in particular the so-called Fadeev-Marcinko potentials, which are integrable on the line with this special weight 1 plus modulus x. Then actually what we discussed before could be generalized to these wider class as well. In particular, we can introduce Yost solutions which are no longer explicit exact exponentials at plus minus infinity, but they are asymptotics to these exponentials. They, as before, can be used to introduce the scattering and reflection, scattering coefficients, that is reflection, transition, and so on and so forth, and so on. For these larger class of potentials, we also have finitely many negative eigenvalues and can introduce the corresponding norming constants. And therefore, in that class of potentials, we can prescribe to every potential Q a triple of the so-called scattering data, which consists of reflection coefficient from the right or from the left, it doesn't matter actually, the set of bound states, that is negative eigenvalues, and the corresponding norming constants. This is the direct scattering task from potential, from the operator, describe the scattering data, but a natural inversion of this is the so-called inverse scattering problem or inverse scattering task, which tries for a given prescribed set of scattering data to reconstruct the potential Q itself. This is possible due to very nice theory due to Marcinko and Fadeev, and developed, well, there are several approaches actually by Gelfand, Levitan, and Krein in 50s, in addition to that by Marcinko. But in general, they completed the whole theory of scattering theory for Schrödinger operators in that class. Namely, they gave a complete characterization of these reflection coefficients and scattering data and suggested an efficient algorithm to determine Q from the scattering data. And I, again, briefly can recall how this theory works. So the main idea is that the potential Q is related to the scattering data through the so-called Marcinko equation. And here is some ingredients. It turns out that the Yost solution could be written in a very special form as a transformed unperturbed solution, which is the pure exponential. Namely, there is an integral transformation, integral operator of Volterra type with some kernel k of xt, so that the Yost solution can be written in this integral form. And it turns out that these kernel k of xt is related to the special function f, some function f, which is in fact the Fourier transform of the scattering data in this sense, in the sense that it consists of two summands. The first is indeed the Fourier transform, and the second also could be viewed as a Fourier transform of the discrete part of the spectrum, where we put a delta function at the point minus kappa with intensivity, with mass alpha j. So anyway, given scattering data R plus, alpha, and kappa, we can form this function f plus. And then it turns out that this f plus is related to the integral kernel k plus through the so-called Marcinko equation written here. This is Volterra type, second type Volterra equation, which has a unique solution for every fixed x, and therefore we can solve it. If we have f, we can solve it for k, and then using this k, it turns out that the potential q, initial potential q, is recovered simply as minus two derivatives of this integral kernel restricted to the diagonal. Of course, there are many steps that need justification, but that was all done in the last century, and basically this is the complete theory of inverse scattering, direct and inverse scattering transform scattering problem for Schrödinger operators with Padaev-Marcinko potentials. By the way, I'm talking and talking and talking, but if you want to ask questions, then of course you can interrupt me at any time. So, and here is an interesting field of research. As we have seen, there is a very nice relation between these inverse scattering theory for Schrödinger operators and the problem of finding solutions for the KdV equation. So there is some very nice connections of these tasks.
May I have a question to the inverse scattering? So this was scattering on the line.
On the line.
One can also imagine scattering on the half line.
Yes.
So is there an analog of inverse scattering on the half line?
Yes, certainly. Inverse scattering on the half line is also well understood problem, and there is a complete analogy to what I explained about the whole line case. And certainly there are also there is KdV on half line.
What are the scattering data? I mean,
oh yeah, these are slightly written slightly differently. So the setting is slightly different here. It's the called F phase of the wave, so to say, for instance. Yeah, so this is not complete analogy in physical sense, but I was talking about the complete mathematical analogy. So physically, the Yost solution comes to the origin with some values. And we can use these boundary values of the Yost solution to define analogs of these reflection and transition coefficients, if in vague terms, how the analogy works.
Thank you. Okay, yeah. Thank you.
Mm-hmm. Okay, good. So given these relation, a natural question is if we can, or natural a natural attempt is to try to generalize or to extend the inverse scattering theory for Schrödinger operators in the hope that it will give us the possibility to find solution to a larger class of KdV equations. Yes, because this Padaev-Marcinko theory certainly restricts the the class of solutions, we can get to only this Faddeev-Marcinko class. So it means that we only have to look at the initial conditions, conditions for these KdV from that class. If we are able to generalize the inverse scattering theory, automatically we would be able to, or we hope to be able automatically enlarge the class of initial data for the KdV equation, and therefore have this theory expand work to a much larger class of potentials. So in particular, a natural attempt is to try to include a standard for quantum mechanics singular potentials like delta potentials or other distributions. They are widely used to describe various models of quantum mechanics, and therefore it would be nice if the theory would work for such larger class. Or we saw another restrictions that there in this Marcinko class of potentials, there are only finitely many eigenvalues, bound states possible. But some natural models, like for hydrogen atom, have infinite negative spectrum. Therefore, it's interesting if anything can be done with potentials, with operators possessing infinitely many negative eigenvalues. Well, one short remark is that there are certainly certain bounds for such a generalization. For instance, it cannot work for any L2 potential just because L2 potential are known to create non-trivial singular continuous spectrum in addition to absolutely continuous part, and therefore this rules out automatically possibility of extending this inverse scattering theory. But still, it would be interesting to find some natural boundaries up to which we can generalize the theory. And I actually now briefly describe what we did in one direction, in a direction of weakening smoothness assumptions on the potentials, and explain why it didn't give us any progress or we could not apply that to the KdV equation. And then on the more positive side, we'll try to generalize the other part. So this is generalizing, so to say, the continuous part of the spectrum. But now it is possible also to allow infinite negative spectrum, and this is indeed what allows us to build corresponding generalization to the soliton solutions of the KdV equation, which I explained in the third and last part of the talk. So briefly, the idea which actually allowed us to include delta type potentials into the classical scattering theory for Schrödinger operators due to, as I said, Faddeev-Marcinko and many other famous contributors, was in a remark, or was based on the result by Miura, who observed that there is a very nice transformation, the so-called Mura transformation, which relates solutions of the standard KdV and modified KdV equations. Standard and modified KdV equations, as you can see, differ very, very little. Well, there is plus minus signs interchange, and also here we have a square, and here is just Q. But anyway, the structure is quite similar. But important thing is that was this observation by Mura that given a solution family for MKDV and applying this transformation B gives us the solution to the standard KDV equation. For us, a crucial thing was the form of this transformation, because actually, if Q is given as U prime plus U square, it means that the corresponding Schrödinger equation can be factorized. It is factorized as two linear terms, I mean first order terms. And in particular, this shows that such an operator is a special case of the Dirac-O'Krine system. Okay, and it turned out that using this very special structure of this Schrödinger operator it allowed us to indeed generalize the theory far beyond the classical Faddeev-Marcinko equations. In particular, we showed that if we consider, if we take these functions U from this class, and as you remember, the potential Q is U prime plus U square, it means that this Q can be a derivative of an L1 function, so it's already a distribution, not arbitrary, but still it may be a distribution. And it turns out that if U is in L1 cap L2, there is a very nice analogy of or we can push forward main steps in the classical scattering theory and make it work for this enlarged class of potentials. So I may skip the mathematical part and just give you an illustrations of a few examples of potentials which are included into this larger class and for which the complete direct and inverse scattering theory is possible. For instance, if taking U of this form and playing with parameters alpha and beta, guaranteeing that it is in the required class, and then calculating the U prime plus U square, we see that this resulting potential Q actually oscillates and grows at plus minus infinity. So it's highly oscillating, growing potential for which one would not expect scattering theory, but still it turns out that it has absolutely continuous spectrum and scattering reflection coefficient can be introduced as well in a natural way, and these can be used to reconstruct the potential itself. If we take the indicator of some interval, then the resulting Q will be the combination of delta functions already. Yes. However, if we try to represent delta function itself in this form, it turns out that it is not possible with view of the specific of the required class. We can have two different solutions of this Riccati equation. One which is nice at plus infinity, and here nice means it's identically zero, so it satisfies this integrability condition. But the part at on the negative half axis is not in L1, is not integrable. Or we could take the counterpart, which is identical zero at negative part, but is not integrable at plus infinity. So these are two typical solutions to this Riccati equation, and we see that unfortunately delta cannot be represented through this Miura transformation with U, which is in this L1 cap L2 on the whole line. However, this was our motivating example to enlarge these class of Mura potentials even more. We then weakened the requirements and allowed two different Riccati representations, on one which is good on positive half line, one which is good on negative half line. Use say U plus to reconstruct Q on the positive half line, use U minus to reconstruct on the negative half line, and then prove that actually these two reconstructed pieces match very well. And these enlarged class already included delta X. That's how we design it. That's was our motivation. But it turns out that by doing that, we increased the class of potentials for which meaningful direct and inverse scattering theory exists quite essentially. For instance, if we have this Miura 1, so to say, potential and add to it some distribution from negative Sobolev class H minus 1, which is of compact support, then if the sum is non-negative, then the sum is again in this Miura 2 class. In addition, every positive Fadeev-Marcinko potential is also included here. So it's indeed a generalization of the theory. However, if you remember, this Riccati representation of the potential resulted in a very special form, factorized form of the Schroedinger operator. So it was like minus second plus U, and the same with minus U, and that automatically implied that the corresponding operator, Schroedinger operator S, was non-negative. So in particular, both these classes did not allow negative eigenvalues, bound states. However, the next step was to show that actually this is not a restriction, and in fact, we can include any number of negative bound states, for instance, using this double commutation technique. And it turns out that indeed, roughly speaking, we can start with Fadeev-Marcinko potential and add to it any singular piece of compact support from H minus 1, and it will possess inverse, direct and inverse scattering theory. So we can define all scattering data for it, and moreover, using our approach, we can reconstruct them from the data. The natural question is that, okay, once we have succeeded in pushing forward these boundaries for inverse scattering transform, could we also automatically solve KdV, or rather MKdV in this context? Unfortunately, the answer to this is no, just because the evolution of KdV flow actually automatically kicks out our initial condition from the considered class out. Yeah? So unfortunately, although we were successful in extending the class of potentials, including the scattering theory, however, this didn't help us to solve KdV for a larger class of initial data using these original approach of Gardner, Green, Kruskal, and Mura.
Excuse me.
Yes, please.
This larger class, this is larger mostly in terms of local singularities, or also in terms of decay at infinity?
Both. Maybe I return to that example I had. So the first example was this one. So this is a potential which actually is unbounded at infinity. It grows and oscillates, highly oscillating, growing potential. You see, so this is neither bounded nor regular at infinity. So it highly oscillates.
Thank you.
So it's very weird, but due to special structure, it has scattering data, well-defined scattering data, and moreover, we can use this scattering data to reconstruct Q. The point is, of course, that we don't reconstruct Q, we rather reconstruct U in our approach, and then differentiate U, and this makes Q so weird. But yes, but still, in terms of Q, it's indeed quite non-trivial behavior, which would not be expected at all.
Yeah. So it may grow at infinity, but then it has to oscillate very much. Is it?
Well, not exactly. Well, yes. If we take just U, which is decaying, so U prime determines the behavior at infinity. If we want growing potential, then of course we should think of a function U in L1, which after differentiation gives us this behavior. So this is one of the possibility. Maybe we can take some, also include some other type of dependence. I'm not able to answer your question, very interesting question right ahead, but yes, so you see an example of this. So it is both in local singularity, like including delta functions, finitely many delta functions, for instance, and also having more weird, so to say, behavior at infinity. So in particular, decaying to zero is no longer required, or rather is no longer necessary, so to say. Okay, so now, as you remember, there were two parts in this scattering data. Part which was the reflection coefficient and which was characterization, roughly speaking, of the continuous spectrum, and then negative part, which were negative bound states and these norming constants. Then another possibility is to just try to play with these bound states and to make the continuous part, this reflection coefficient, standard, smooth. For instance, let's take the simplest possible case of reflectionless potential where R is identical 0. This is very important case, of course, with many physical important applications. Historically, the first examples of such reflectionless potentials were due to Bargmann, but later on, in 1956, I.Kay and H.Moses actually suggested the unified approach, which produced all classical, that is Fadeev-Marcinko class reflectionless potentials. And let me briefly outline how they proceeded, how they did that. If you remember, in Fadeev-Marcinko equation, there was this function f plus, which contained two parts, Fourier transform of R plus and Fourier transform of the discrete part. So if R plus is 0, then we don't have these piece, and therefore f plus is only this linear combination of pure exponentials. And actually, if we take f plus of this form, that then the Fadeev-Marcinko equation is actually reduced to a system of linear equations for solution which is necessarily of this form. So we are left of linear equation, and therefore we can solve it, and there is a closed form solution, which is what Kay and Moses did. So they therefore represented these reflectionless potentials in this closed form, where you can recognize here these alphas. These are norming constants, and bound states are minus kappa j squared. But in the formula, we have a positive kappa j. Okay, and so this is a general formula, generic formula describing all reflectionless potentials. And it turns, in particular, if we take just one for n equals to 1, we get this very nice formula. We see that this is a very smooth analytic function which decays very fast to 0 at plus exponentially fast plus minus infinity. Okay. It turns out that these special reflectionless potentials, when plugged into this KdV flow for scattering data, results in what we call the n-soliton solutions of KdV. So basically we have, I showed you a picture of two solitons moving with different velocities and interacting and passing through with some shift in phases. This is just n-dimensional generalization of this formula. What is different here is just, as you remember, in this KdV flow, kappas, the bound states, are fixed. They don't change with time, but alpha got some factors, and this factor actually appears here. So this is n-soliton solutions. Yeah. Classical n-soliton solutions, and it is certainly a natural question is if we can enlarge the class of these classical n-soliton solutions to get something more interesting. And one of the attempts was made by Fritz Gastesi and co-authors, who back in '92 suggested a very simple approach. So they said, okay, let's just take, let n go to infinity. So let's take more and more eigenvalues and bound states and look if probably a reasonable limit exists. And they indeed succeeded in that, and derived, along with many other interesting results, the complete analog of Kay-Moses formula. The only difference is that in Kay-Moses case, we had a matrix, n by n matrix, but now we have the determinant of operator in little L2, so this is already an infinite matrix, so to say. Yeah, so this C of X is a matrix with entries which are as before. So the only thing that changed is that we allowed n to be infinity. Of course, one has to justify that this formula makes sense and understand when it makes sense, and so on and so forth. In particular, but they succeeded in doing that, and they showed that actually kappa j can be an arbitrary bounded sequence of pairwise distinct positive numbers, and alphas also are positive numbers, but to make everything work, they impose the following restrictions under which the passage to the limit was actually possible. Marcinko had suggested in 91 suggested slightly different approach. He just considered the he studied the closure of the set of all potentials with fixed boundary on the minus kappa square on the negative spectrum in the topology of uniform convergence on compact sets, and showed that in the limit one also gets a potential which can be called reflectionless, and actually it generates the corresponding solution to the KdV equation, which also has a complete analogy of these inverse scattering transform approach of Gardner, Green, Kruskal, and Mura, and so on. However, in addition to, he has more mathematical approach, which was based on the so-called Weil-Titchmarsh functions for the corresponding Schrödinger equation, and worked in these terms, and in terms of the so-called spectral measure related to the Schrödinger operator. However, one of the weak points of this approach is that the characterization in terms of this spectral measure is very implicit. So is not explicit. Yes. So there is not a clear way how to derive properties of one object of the potential, for instance, based on the spectral measure. Okay. Therefore, what we posed as the main questions for our research is it possible to follow the approach or the idea of the approach of Gastesi and co-authors, but try to give a complete characterization of all the potentials we can get, and transfer that to the solutions of the KdV equation. In particular, it is natural to restrict ourselves to these generalized reflectionless potentials, which are which have some integrability, for instance, in LP classes. So this intersection, which we call QP, is in fact closed in the respective LP space. Also, it has probably infinitely many negative eigenvalues which go to accumulate at zero. Yes, but also for every eigenvalue we can define in a standard way the corresponding norming constant. So there is a hope that the theory can be transformed, transferred, enlarged to this class of potentials. In particular, we would like to understand the properties of the mappings which to every potential Q in this larger class prescribes the set of the eigenvalues, or rather these square roots of minus eigenvalues, kappas, and the corresponding sequences of norming constants. So there is a natural scattering map associated with every Q in this class. As we said, to every Q, we prescribe the sequence of these kappas related to bound states and alphas of norming constants.
Excuse
so
me.
The question, yes?
Excuse me. What does this subscript CL mean? Classical.
This is classical. If we remove classical reflectionless potentials, we guarantee that there are infinitely many eigenvalues. Otherwise, there are
classical potentials means those obtained by the formula that was
K and Moses.
Okay.
So there is closed formula for that. Nothing interesting. Well, at least from this perspective, the question is closed. There is explicit formula for set of potentials. And if you take these as initial data in the KdV, we have an explicit formula for the solution to that KdV.
And so classical in particular means that there are a finite number of these solitons.
Yes, exactly. That's exactly the case of n soliton solutions. So we get n soliton solutions this way.
Yes,
Classical.
so you want to have an infinite number of
Yes,
of
exactly.
solitons.
So our aim was to make a very complete description of infinite solitons, so to say, within some class of initial data that is of potentials.
Mm-hmm.
Okay. So there are some information on kappas, for instance. Due to the Lipschitz-Thirring inequality, we know that kappas, if you take potential from LR with some R, then kappas fall into LP with P related to R through this formula. So in particular, for P equal 1, we know that the sequence of kappas will automatically be summable. Okay. And then a natural question is that if we can get any summable sequence of kappas from the negative spectrum of the some reflectionless potentials. In other words, if every kappa is realized, and if so, what is, for instance, the isospectral set of potentials? So if we fix the bound states, how much freedom do we have in these in respective reflectionless potentials? In particular, how can we describe the set of these norming constants? Okay. And here is our result for P equal to 1. As I said, for P equal to 1, we have the clearest picture. First question about whether, roughly speaking, every kappa can be obtained was answered already by Gastesi and co-authors. But we gave a complete answer to questions 2 and 3 in this case. And here are 2 papers where this can be done. Our main result is that this scattering mapping from the class of summable reflectionless potentials, that's what this subscript 1 means, is injective and onto this set. L1 plus means the set of all strictly decreasing sequences in L1, which consist of positive values. So that's how we parameterize the negative eigenvalues. So everything can be obtained here. But the most surprising result was that there is absolutely no restrictions on possible norming constants. So a sequence of alphas is absolutely unrestricted. In particular, it may grow to plus infinity or behave. We can take whatever we want. This is a very unexpected result. At least it was very unexpected for us. Briefly, how we got it. Our approach was very simple. So as you remember, I said that Gastesi and co-authors took the formula of K and Moses and tried to generalize it to infinite number of negative bound states. But this formula of K and Moses, and maybe I jump to somewhere here to show it, this formula of K and Moses resulted as a solution to this Marcinko equation, which actually can be written as a system of linear equations. So this formula is just Kramer rule to solve these equation, linear system. But we decided not to use the Kramer rule and respectively not to work with determinants, but rather just solve the resulting system by inverting the matrix. So you see, we have the system of the form identity plus some operator m of x applied to some vector f is vector g, for instance. Instead of using Kramer rule, we just said, let's invert this matrix. It is invertible because m of x is non-negative. Let's try to generalize this approach to operators. Okay, and that's what we did. So our setting was the following. So we worked in little L2 class rather than in CN as it was in I.Kay and H.Moses. And we just replicated the ideas which led to that system of equations and replaced it by the operator equality, and said that let's just represent this solution in let's solve the system by inverting the operator. It is invertible. That can be proved. But more exactly, after several transformations, what we got is the formula for the primitive of the potential Q of this form. It takes form of squared norm of some vector, and in this vector you see the inverse of some operator, or the inverse squared root of that. That's the most general form of the solution, and despite the maybe you may think that this is a quite hard formula, which is hard to get analyzed. However, it turns out that from this formula we can derive many important properties of this potential Q. In particular, this potential Q will be analytically continued and extended into the whole strip, complex strip around the real axis. And moreover, the corresponding Schroedinger equation indeed can be shown to possess the required bound states, required spectra, and the value as alpha we prescribed will be the norming constants. And moreover, the operator, the potential with this set of scattering data is unique, as we already mentioned. Moreover, just by formally using the flow, KdV flow for evolution of the scattering of the norming constants. If you remember, there was this exponent of kappa cubed t factor. So in operator terms, it just means that instead of taking operator A, we consider the operator family A of T of this form, and then just plug in that A of T into the formula we had before to get the time-dependent family of potentials, which turn out to give us the solution to the KdV equation. So more exactly, the solution is two times the derivative of Q. So this U is in fact a generalized soliton solution to the KdV equation. One can prove directly that this formula can be differentiated in x and t in the classical sense, and the function u is indeed this classical solution. to the KdV, which moreover allows extension in the complex domain, both in around spatial variable x and time. So this is a complete analogy to the n-soliton solutions. Okay? So a general idea of the approach is, of course, there are many mathematical obstacles which we had to overcome on this way, but still we succeeded in getting all pieces together and having these general description of possible reflection of all integrable reflectionless potentials and the corresponding integrable generalized soliton solutions to the KdV equation. So once again, what we got is the complete description and the explicit way of describing all integrable solitons, generalized soliton solutions to the KdV equation this way. On the way, there were several nice separate tasks like uniqueness reconstruction in the scattering task by 3 spectra, which has analogs in and is of separate interest to interscattering theory. But as I said, the main thing is a complete characterization of all integrable soliton solutions to the KdV, a complete characterization of all integrable reflectionless potentials, and this nice very simple formula, which despite very abstract form, is very convenient to work with. I would dare to say it's more convenient to work with than this formula through generalized determinants, which was used by Gastesi and co-authors. On this, let me stop. I'm sorry, I took more of your time than were allowed. Thank you.
Thank
for
you.
your attention.
Thank you so much for your talk. Are there any questions, comments?
May I have a question?
Sure, go ahead.
So you mentioned that one can get any sequence of norming constants. I mean, whatever going to infinity in any way. So correspond to positions of solitons or to their intensities, or
I missed part of your question due to bad connection, but yes, thank you for this nice question. Indeed, if you let me jump to I tried to jump to the correct, oh no, that was next one, yes. So the case n equal 1 is indeed very instructive because it shows how this norming constant is involved into the solution. Despite the intuitive belief that it should correspond to the amplitude or whatever, it is actually responsible, so to say, for the phase. And one can see this from, I deliberately made it in blue, from this way of determining x naught. So x naught, the phase or the shift, yes, is related to the norming constant this way. And so A1 does not contribute to the amplitude, to the factor. Amplitude is completely determined by kappa, by the bound states. Moreover, the velocity will also be determined by kappa alone, yes, rather than by alpha. So alpha is responsible to the phase shift. By the way, what I said about velocity is maybe not completely correct, because if you remember, we should replace alpha by something like alpha times e to the power 4 kappa cubed t. So if you try to plug this here and recalculate x naught, it will bear something from this alpha. Yeah.
Thank you.
So now it explains why if you have, say, that picture with two solitons, soliton of higher amplitude moves faster, because amplitude is determined by kappa, and kappa is also responsible for the phase shift, for the phase speed. So higher waves move faster. Okay. But yes, returning to your questions, no restrictions of alpha, although very unexpected from the beginning, is more or less consistent with this analysis of n=1 case, so that alpha just contribute, not just, but contribute more to the phase than to the amplitude. Or however, this is highly non-linear, highly non-trivial, and difficult to understand directly from those.
Okay. Are there any more questions, comments? Okay. Yes.
Yaroslav, do I understand you correctly that the spectrum is absolutely continuous? Positive part is absolutely continuous. There is there are no embedded eigenvalues.
Yes, that's true. That's true for all these reflectionless potentials. There are no embedded eigenvalues.
Yes, but in your case, is also no.
Yes, as I said, reflectionless potentials do not have embedded eigenvalues, because reflectionless potentials, they are actually very well behaved at infinity. So, for instance, n-soliton solutions, as I said, they decay exponentially fast. Generalized reflectionless potentials, of course, no longer are exponentially decaying, because, as I said, we can get just what we get is just L1 decay, not exponential decay.
This is enough.
Yeah, but then there is no embedded eigenvalues in the absolute, no singular continuous spectrum, of course, and no embedded eigenvalues. Yeah.
Okay, and maybe one more question. This is this class of Mura potentials. Do you know the spectral theory of this class? You mentioned that it is not invariant.
Yeah, what do you mean?
Spectral
theory?
I mean, absolutely continuous, embedded eigenvalues, singular spectrum, and so on.
Oh yes, certainly. It's the picture is very clear. Look, what I mentioned is that Mura potential lead to non-negative Schrödinger operator. But I later mentioned also that we can add finitely many by double commutation method, for instance, and that's not the crucial point. But basically, these also have absolutely continuous spectrum and no embedded eigenvalues on positive half line. Otherwise, just this inverse scattering theory would not work. It's not known how to reconstruct, or if in the presence of singular continuous spectrum, how we can reconstruct the potential. As far as I know, there is no understanding, no clear understanding of this. There is some attempts to do that for the trine systems, and there is a very nice work by Denisov, and also Terence Tao also studied this question, although in slightly different contexts. But how can we use this singular continuous part of the spectrum or the spectral measure to reconstruct the operators? But as far as I understand, there is no complete theory or complete understanding of this.
Yes, thank you.
Thank you. Any more questions? It does not seem to be the case. So let's thank our speaker again for this very nice talk.
Thank you.